whitewash the laws of thermodynamics and entropy. Good evening. Tonight we will be covering the laws of thermodynamics and entropy. We will proceed at a measured and deliberate pace, as this subject deserves careful, thorough, and systematic treatment. The material we are about to discuss was developed over the course of several decades in the 19th century, primarily through the foundational contributions of Rudolf Julius Emanuel Clausius, a German physicist and mathematician who lived from the 2nd of January, 1822 to the 24th of August, 1888, and of William Thomson, who is more commonly known by his title, Lord Kelvin, a Scottish-Irish mathematical physicist and engineer who lived from the 26th of June, 1824 to the 17th of December, 1907. We will also acknowledge the contributions of James Prescott Joule, Nicolas Leonard Sadi-Carnot, and Ludwig Edward Boltzmann, among others, as they will appear naturally and organically in the course of our discussion. This is, as I say, a very thorough treatment, and we will not rush any portion of it. Let us begin by situating ourselves historically and conceptually, so that when we arrive at the formal statements of the laws, we understand not merely the words, but the long and painstaking intellectual journey that produced them. Further preliminary remarks, the nature of heat, and the development of thermodynamics. In the early part of the 19th century, there was still considerable scientific confusion about the nature of heat. The prevailing view, associated with the work of Antoine Lavoisier and others, was that heat was a subtle, weightless fluid called caloric, which flowed from hotter bodies to cooler ones. This caloric theory was not without merit. As a phenomenological description, it successfully accounted for many observations about heat flow, but was fundamentally incorrect as a physical model. The caloric theory began to be seriously undermined by the experimental work of Benjamin Thompson, Count Rumford, who in 1798 demonstrated through his observations of cannon boring that the amount of heat generated by friction appeared to be essentially unlimited, and therefore could not plausibly be attributed to the release of a finite quantity of stored caloric fluid. The heat, Rumford noted, appeared to be generated continuously so long as the boring continued, which was difficult to reconcile with the idea of a finite caloric substance being released. This was a significant and troubling observation for proponents of the caloric theory, and it planted a seed of doubt that would take several more decades to fully germinate. It was James Prescott Joule who, through his meticulous and painstaking experiments conducted through the 1840s, established with quantitative precision the equivalence of mechanical work and heat. Joule's paddle wheel experiment, in its most refined form, involved a known quantity of water contained in a calorimeter, through which a paddle wheel was driven by falling weights of known mass, falling through a known height, and the resulting temperature rise of the water was measured carefully. From these experiments, Joule determined what we now call the mechanical equivalent of heat, that is, the amount of mechanical work required to produce a given quantity of heat. The modern value of this equivalence is that one thermochemical calorie is equal to approximately 4.184 joules, where the unit of energy known as the joule is, of course, named in his honor. This is the relationship that would eventually be expressed as the first law of thermodynamics, known as the zeroth law of thermodynamics. Before we address the first, second, and third laws in their proper order, we must briefly address what is known as the zeroth law, so named because it is so fundamental that it is logically prior to the other laws, even though it was formally stated after them. The zeroth law was articulated most clearly by Ralph Howard Fowler in 1931, though its content was implicitly assumed throughout the development of classical thermodynamics. The zeroth law of thermodynamics states that if two thermodynamic systems, which we may call System A and System B, are each in thermal equilibrium with a third system which we may call System C, then System A and System B are also in thermal equilibrium with each other. In other words, if A is in thermal equilibrium with C, and B is in thermal equilibrium with C, then A is in thermal equilibrium with B. This statement, seemingly obvious, is actually the logical foundation for the concept of temperature as a transitive, measurable property. It is what allows us to use thermometers, the thermometer being our system C, to compare the temperatures of different systems. Without the zeroth law, the concept of temperature as an objective, universal property would not be well defined. The zeroth law allows us to say that temperature is a property of a system, and that two systems in mutual thermal equilibrium share the same temperature. This is the foundational concept, and it underpins everything that follows. Tunwin. The first law of thermodynamics. The first law of thermodynamics is, in essence, a statement of the conservation of energy as applied to thermodynamic systems. It tells us that energy is conserved. It cannot be created from nothing, nor can it be destroyed. It can only be transferred or converted from one form to another. This is a principle that will be stated several times in slightly different ways, because it is important that its meaning be fully absorbed. The formal statement of the first law is as follows. The change in internal energy of a closed thermodynamic system is equal to the heat added to the system minus the work done by the system on its surroundings. In symbolic notation, this is written as delta U equals Q minus W, where delta U represents the change in internal energy of the system, Q represents the heat transferred into the system, and W represents the work done by the system. We may also write this in differential form, the infinitesimal change in internal energy, written as du, equals the infinitesimal heat added, written as delta Q minus the infinitesimal work done by the system, written as delta W. It is important to note the sign convention here, to be precise about it, because different textbooks use different conventions. And the convention we are using here, which is the physics convention, and the convention used by most thermodynamics textbooks, in the tradition of Tsemansky, Q is positive when heat flows into the system, and W is positive when work is done by the system. Some engineering texts use the opposite sign convention for work, in which case the first law is written as delta U equals Q plus W, where W represents work done on the system. We will use the physics convention throughout this lecture, so that W represents work done by the system. The internal energy U of a system is a state function, A. This means that its value depends only on the current thermodynamic state of the system, characterized, for example, by its temperature, pressure, and volume, and not on the path by which the system arrived at that state. This is a very important distinction, and it bears repeating. Internal energy is a state function. Its change, delta U, depends only on the initial and final states, not on the process by which the transition occurred. Heat Q and work W, by contrast, are not state functions. They are path functions or process quantities, meaning that the amount of heat transferred and the amount of work done depend on the specific process or path taken between two states. This is why we write delta Q and delta W with the symbol delta rather than D, to distinguish inexact differentials which are path dependent from exact differentials like du, which are path independent. This distinction between state functions and path functions is one of the subtler and more important conceptual points in classical thermodynamics, and it is one that students sometimes find confusing at first encounter. For a simple compressible system, such as an ideal gas in a cylinder fitted with a piston, the work done by the system is given by the integral of pressure with respect to volume, specifically the work done by the gas as it expands from volume V sub 1 to volume V sub 2 is equal to the integral from V sub 1 to V sub 2 of P dV, where P is the pressure of the gas. In verbal form, W equals the integral from V1 to V2 of P with respect to V. For a process carried out at constant pressure, which is called an isobaric process, This simplifies to W equals P times the quantity V sub 2 minus V sub 1, or equivalently W equals P times delta V. The first law tells us, among other things, that a perpetual motion machine of the first kind, that is, a machine that produces useful work output without any energy input, creating energy from nothing, is impossible. Such a machine would violate the conservation of energy, and no such machine has ever been constructed or demonstrated to function, despite many attempts throughout history. The impossibility of such a device is the practical content of the first law. Different types of thermodynamic processes have different relationships between heat and work under the first law. In an isothermal process, the temperature remains constant. For an ideal gas undergoing an isothermal process, the internal energy, which for an ideal gas depends only on temperature, remains constant as well, meaning delta U equals 0, and therefore Q equals W. All the heat added to the system goes into doing work, or all the work done on the system is expelled as heat. In an adiabatic process, no heat is transferred, Q equals 0, and therefore delta U equals negative W. The change in internal energy is equal to the negative of the work done by the system, meaning that if the system does work, its internal energy decreases, and if work is done on the system, its internal energy increases. In an isochoric process, the volume remains constant, so W equals 0, and therefore delta U equals Q. All the heat added goes into changing the internal energy of the system. And the Carnot cycle, and the motivation for the second law. Before stating the second law formally, it is instructive and historically accurate to discuss the work of Nicolas Léonard Sadi Carnot, a French military engineer who lived from the 1st of June, 1796 to the 24th of August, 1832. In his remarkable monograph of 1824 titled Réflexions sur la puissance motrice du feu, which translates to Reflections on the Motive Power of Fire, Carnot analyzed the theoretical maximum efficiency of heat engines, that is, devices that convert heat into useful mechanical work. It is remarkable and worth emphasizing that Carnot carried out this analysis still within the framework of the caloric theory, and yet arrived at results that are entirely correct within the framework of modern thermodynamics. This speaks to the power of careful theoretical reasoning, even when some of the underlying assumptions are incorrect. Carnot considered an idealized reversible heat engine operating in a cycle between two heat reservoirs. A hot reservoir at a high temperature, which we denote T sub H, and a cold reservoir at a low temperature, which we denote T sub C. The idealized cycle he described, which now bears his name as the Carnot cycle, consists of 4 reversible processes. First, an isothermal expansion at the high temperature T sub H, during which the engine absorbs heat Q sub H from the hot reservoir. Second, an adiabatic expansion, during which the temperature of the working substance drops from T sub H to T sub C. Third, an isothermal compression at the low temperature T sub C, during which the engine expels heat Q sub C to the cold reservoir. And fourth, an adiabatic compression, during which the temperature of the working substance rises from T sub C back to T sub H, returning the system to its initial state and completing the cycle. The efficiency of a heat engine is defined as the network output divided by the heat input from the hot reservoir. Symbolically, efficiency, denoted by the Greek letter ETA, equals W net divided by Q sub H. By conservation of energy, the first law, the network output is equal to the heat absorbed from the hot reservoir minus the heat expelled to the cold reservoir. W net equals Q sub H minus Q sub C. Therefore, eta equals the quantity Q sub H minus Q sub C divided by Q sub H, which simplifies to eta equals 1 minus Q sub C divided by Q sub H. Carnot argued correctly that no heat engine operating between two reservoirs at temperatures T sub H and T sub C could be more efficient than a reversible engine operating between those same temperatures. This is Carnot's theorem. The efficiency of the Carnot cycle, expressed in terms of temperature, is eta sub Carnot equals 1 minus T sub C divided by T sub H, where the temperatures are measured on an absolute scale. that is, on the Kelvin scale. The Kelvin scale is indeed named after Lord Kelvin, who used Carnot's work to define an absolute temperature scale that is independent of the properties of any particular substance. This is the thermodynamic temperature scale, and 0 Kelvin represents the absolute lowest temperature, the temperature at which all classical thermal motion would cease. It follows from Carnot's efficiency formula that a perfectly efficient heat engine, one that converts all of the heat input into useful work, would require either that T sub C equals 0 Kelvin, which, as we shall discuss, is unattainable, or that T sub H approaches infinity, which is equally impractical. In any realistic engine, T sub C is greater than 0 and T sub H is finite, and therefore the efficiency is always less than 100%. Some heat must always be expelled to the cold reservoir. The second law of thermodynamics. The second law of thermodynamics is, in many respects, the most profound and far-reaching of the thermodynamic laws. It introduces a fundamental asymmetry in time, a direction to physical processes that is not present in Newton's laws of motion or in the first law of thermodynamics. The second law tells us why certain processes occur spontaneously in nature, while their time reverses do not, why heat flows spontaneously from hot to cold and not from cold to hot, why gases expand to fill their containers and do not spontaneously contract, why useful energy tends to degrade into heat. The second law has several equivalent formulations. We will present 3 of the most important. The first formulation is the Kelvin-Planck statement, which may be stated as follows. It is impossible to construct a device that operates in a thermodynamic cycle and produces no effect other than the transfer of heat from a single reservoir and the performance of an equivalent amount of work. In simpler terms, it is impossible to convert heat completely into work in a cyclic process. There must always be some heat rejected to a cold reservoir. A perpetual motion machine of the second kind, one that extracts heat from a single reservoir and converts it entirely into work without any other effect, is impossible. This statement encapsulates the practical lesson of the Carnot analysis. Some portion of the heat input must always be expelled as waste heat. The second formulation is the Clausius statement. It is impossible to construct a device that operates in a thermodynamic cycle and produces no effect other than the transfer of heat from a cooler body to a warmer body. In other words, heat does not flow spontaneously from a cold body to a hot body. Refrigerators and heat pumps can move heat from cold to hot, but only by doing work on the system. They require an external energy input, and they are not in violation of the Clausius statement because they do produce another effect, namely the consumption of work. If no work were supplied, no net transfer of heat from cold to hot could occur. These 2 statements, the Kelvin-Planck statement and the Clausius statement, are logically equivalent to each other. If either one is violated, the other is also violated, and vice versa. The third and most general formulation of the second law is stated in terms of a new state function called entropy, which was introduced by Rudolf Clausius in 1865, and the word entropy was coined by Clausius himself, from the Greek word trope, meaning transformation or turning, to parallel the word energy, which comes from the Greek ergon, meaning work. Clausius wanted a word with similar linguistic roots to energy to emphasize the parallel importance of the 2 concepts. Thirtus. Entropy, the Clausius definition. Clausius defined the entropy change of a system undergoing a reversible process as follows. For an infinitesimal reversible process in which the system absorbs an infinitesimal quantity of heat delta Q sub, reversible at an absolute temperature T, the infinitesimal change in entropy ds of the system is defined as ds equals delta Q sub reversible divided by T. In words, the differential change in entropy equals the differential heat absorbed in a reversible process divided by the absolute temperature at which the heat is absorbed. For a finite process in which the system moves from state 1 to state 2 along a reversible path, the entropy change is given by the integral delta S equals S sub 2 minus S sub 1 equals the integral from state 1 to state 2 of delta Q sub reversible divided by T. This is the Clausius definition of entropy change. We note immediately that since entropy S is a state function, a fact that Clausius was careful to establish, the integral on the right-hand side has the same value regardless of which reversible path is chosen between states 1 and 2. Any reversible path between the two states will give the same entropy change. This is consistent with the definition's reliance on a reversible process. To calculate the entropy change between any two states, even if the actual process connecting them is irreversible, we may choose any convenient reversible path between the same initial and final states and integrate delta Q reversible over T along that path. For an irreversible process, the Clausius inequality tells us that the change in entropy of the system is greater than the integral of delta Q divided by T, where the integral is now evaluated along the actual irreversible path. This is the content of the Clausius inequality, which states the cyclic integral of delta Q divided by T is less than or equal to 0, with equality holding only for reversible cycles. In differential form, this is written as ds is greater than or equal to delta Q divided by T, with equality holding for reversible processes and strict inequality holding for irreversible processes. The second law of thermodynamics, in its entropy formulation, can now be stated precisely. For an isolated system, a system that exchanges neither heat nor work with its surroundings, the entropy of the system can only remain constant or increase. It never decreases. The entropy of an isolated system either stays the same if the processes occurring within it are reversible, or increases if the processes are irreversible. In mathematical notation, delta S sub isolated is greater than or equal to 0. This is one of the most important statements in all of physics. It is sometimes called the principle of entropy increase. The entropy of the universe, the ultimate isolated system, is always increasing. Every irreversible process that occurs in nature increases the total entropy of the universe. The universe, in this sense, evolves in the direction of increasing entropy. This gives a thermodynamic arrow of time. The direction of increasing entropy distinguishes the future from the past. Entropy, change in specific processes. Let us now calculate the entropy change for some specific and illustrative thermodynamic processes, working through the calculations with care and precision. Entropy change in a reversible isothermal process. For an ideal gas undergoing a reversible isothermal expansion at constant temperature T from volume V sub 1 to volume V sub 2, the heat absorbed by the gas is Q equals nRT times the natural logarithm of V sub 2 divided by V sub 1, where N is the number of moles and R is the universal gas constant, equal to 8.314 joules per mole per Kelvin. The entropy change is therefore delta S equals Q divided by T equals nR times the natural logarithm of V sub 2 divided by V sub 1. For an expansion, V sub 2 is greater than V sub 1, so the logarithm is positive and the entropy increases. This makes intuitive sense. As the gas expands, it becomes more disordered, occupying more possible microstates. Entropy change for heat transfer between two bodies. Consider a quantity of heat Q transferred irreversibly from a hot reservoir at temperature T sub H to a cold reservoir at temperature T sub C, where T sub H is greater than T sub C. The entropy change of the hot reservoir is negative Q divided by T sub H. It loses entropy because it loses heat. The entropy change of the cold reservoir is positive Q divided by T sub C. It gains entropy because it gains heat. The total entropy change is delta S total equals negative Q divided by T sub H plus Q divided by T sub C equals Q times the quantity 1 divided by T sub C minus 1 divided by T sub H. Since T sub C is less than T sub H, 1 divided by T sub C is greater than 1 divided by T sub H. and therefore the total entropy change is positive. The universe gains entropy as required by the second law for an irreversible process. This is consistent with the observation that this heat transfer is indeed irreversible. Heat flows spontaneously from hot to cold, but not spontaneously from cold to hot. Entropy change in heating a substance. If a substance of heat capacity C sub P at constant pressure is heated reversibly from temperature T sub 1 to temperature T sub 2, the entropy change is given by the integral from T sub 1 to T sub 2 of C sub P divided by T with respect to T. If C sub P is approximately constant over this temperature range, an assumption that is often justified over modest temperature intervals, this integral evaluates to C sub P times the natural logarithm of T sub 2 divided by T sub 1. Again, if T sub 2 is greater than T sub 1, the entropy increases, as one would expect for a warming process. Statistical mechanics and Boltzmann's entropy. The thermodynamic entropy defined by Clausius is a macroscopic quantity. It is defined in terms of heat and temperature, which are themselves macroscopic concepts. Ludwig Eduard Boltzmann, an Austrian physicist who lived from the 20th of February, 1844 to the 5th of September, 1906, provided a profound microscopic interpretation of entropy in terms of the statistical behavior of the vast numbers of atoms and molecules that make up a macroscopic system. Boltzmann's insight was to connect the macroscopic concept of entropy to the number of microscopic configurations, or microstates, that are consistent with the observed macroscopic state of the system. Boltzmann defined entropy through the famous equation that is now inscribed on his tombstone in the Zentralfriedhof Cemetery in Vienna. S equals K sub B times the natural logarithm of W, where S is the entropy. K sub B is Boltzmann's constant, a fundamental constant of nature equal to approximately 1.38 times 10 to the power of negative 23 joules per Kelvin. And W is the number of distinct microstates corresponding to the macroscopic state of the system. The use of W here, from the German word Wahrscheinlichkeit, meaning probability, refers to the thermodynamic probability, not a probability in the usual sense of a number between 0 and 1, but rather the count of the number of microscopically distinct configurations that all look macroscopically the same. This equation, S equals K sub B times the natural logarithm of W, is one of the most celebrated equations in all of physics. It bridges the macroscopic world of classical thermodynamics with the microscopic world of statistical mechanics. It tells us that entropy is a measure of the number of ways in which the microscopic components of a system can be arranged, while giving rise to the same macroscopic appearance. A state with high entropy has many possible microscopic realizations. It is a highly disordered, highly probable state. A state with low entropy has few possible microscopic realizations. It is a highly ordered, improbable state. The principle of entropy increase can now be reinterpreted in statistical terms. Isolated systems spontaneously evolve from less probable macroscopic states, those corresponding to fewer microstates, toward more probable macroscopic states, those corresponding to more microstates, simply because more probable states are, by definition, more likely to occur by chance, as the system's microscopic components randomly rearrange themselves. This is not a violation of any microscopic law. It is simply a matter of overwhelming statistical probability. The reason a gas expands to fill a container is not because there is some force driving it to do so, but because the uniformly distributed state has so many more microstates available to it than the concentrated state that random molecular motion will, with overwhelming probability, drive the system toward that uniformly distributed state. It can be shown through the framework of statistical mechanics developed by Boltzmann, James Clerk Maxwell, and Josiah Willard Gibbs that the Boltzmann entropy, S equals K sub B times the natural logarithm of W is consistent with the Clausius entropy delta S equals the integral of delta Q reversible divided by T, and that the two definitions agree when both are applied to systems in thermal equilibrium, the connection between them establishes that the universal gas constant R equals Avogadro's number n sub A times Boltzmann's constant K sub B, an equation that links macroscopic thermodynamics to the microscopic picture. The third law of thermodynamics. The third law of thermodynamics is associated primarily with the work of Walther Nernst, a German chemist and physicist who lived from the 25th of June, 1864 to the 18th of November, 1941, and who was awarded the Nobel Prize in Chemistry in 1920. The third law is sometimes called the Nernst theorem or the Nernst heat theorem. The third law states that as the absolute temperature of a system approaches 0 Kelvin, the entropy of a system approaches a minimum value, and for a perfect crystalline substance, that minimum value is 0. More precisely, for any isothermal process, the entropy change approaches 0 as the temperature approaches 0. The limit as T approaches 0 of delta S equals 0 of. And for a perfectly ordered crystalline system at absolute 0, S equals 0, which is consistent with the Boltzmann interpretation. At absolute 0, a perfect crystal has only one possible microstate. Every atom is in its lowest energy state and precisely fixed in position. And the natural logarithm of 1 is 0, so S equals K sub B times the natural logarithm of 1 equals 0. And the third law has the important practical implication that absolute 0 temperature is unattainable in a finite number of steps. This is sometimes stated as a corollary of the third law. It is impossible to cool any system to absolute 0 in a finite number of operations, as the system is cooled closer and closer to absolute 0. The entropy changes associated with cooling processes become smaller and smaller, and it requires progressively more work to remove each additional increment of entropy. Reaching absolute 0 would require an infinite number of cooling steps. This is the unattainability of absolute 0. It does not mean that temperatures very close to absolute 0 cannot be achieved. Indeed, through techniques such as laser cooling and adiabatic demagnetization, temperatures as low as a few nanokelvin, that is, a few billionths of a Kelvin, have been achieved in laboratory settings. But the absolute limit of 0 Kelvin itself remains asymptotically unreachable. Thermosynth, the concept of free energy and thermodynamic potentials. From the fundamental laws of thermodynamics and the concept of entropy, we can derive a set of thermodynamic potential functions that are extremely useful in characterizing the equilibrium states of systems and the spontaneity of processes under various conditions. The Helmholtz free energy, denoted A, or sometimes F, is defined as A equals U minus T times S, where U is the internal energy, T is the absolute temperature, and S is the entropy. The Helmholtz free energy is particularly useful for systems held at constant temperature and constant volume. For a system at constant temperature and volume, a spontaneous process will occur if and only if it decreases the Helmholtz free energy. At equilibrium, the Helmholtz free energy is at its minimum value. The Gibbs free energy, denoted G, is defined as G equals H minus T times S, where H is the enthalpy of the system. The enthalpy H is itself defined as H equals U plus P times V, where P is pressure and V is volume. Therefore, G equals U plus P times V minus T times S. The Gibbs free energy is particularly useful for systems held at constant temperature and constant pressure, which include the vast majority of chemical reactions carried out in the laboratory under ambient conditions. For a system at constant temperature and pressure, a process is spontaneous if delta G is negative. The process is at equilibrium if delta G equals 0, and the process is non-spontaneous if delta G is positive. The Gibbs free energy is therefore the thermodynamic quantity that determines whether chemical reactions will proceed spontaneously under ordinary laboratory conditions, and it has enormous practical importance in chemistry and biochemistry. The change in Gibbs free energy for a process at constant temperature is given by delta G equals delta H minus T times delta S. This equation reveals the two factors that drive spontaneous processes: a decrease in enthalpy, which corresponds to the system moving to a lower energy configuration, and an increase in entropy, which corresponds to the system moving to a more disordered configuration. These two factors can work together or against each other, and the temperature T determines which factor dominates. 13. The Maxwell relations. From the four fundamental thermodynamic potentials: internal energy U, enthalpy H, Helmholtz free energy A, and Gibbs free energy G, and the second law of thermodynamics, we can derive a set of four important identities known as the Maxwell relations. These are mathematical identities between various thermodynamic partial derivatives, and they are useful for relating quantities that are difficult to measure directly to quantities that are easier to measure experimentally. The four Maxwell relations are derived from the equality of mixed second partial derivatives, a mathematical consequence of the fact that U, H, A, and G are all state functions, and therefore their mixed second partial derivatives are equal regardless of the order of differentiation. From the fundamental relation du equals TdS minus PdV, the Maxwell relation is the partial derivative of t with respect to v at constant s equals the negative of the partial derivative of p with respect to s at constant v. From the relation dh equals tds plus v dp, the Maxwell relation is the partial derivative of t with respect to p at constant s equals the partial derivative of v with respect to s at constant p. From the relation dA equals negative s dt minus p dv, the Maxwell relation is the partial derivative of s with respect to v at constant t equals the partial derivative of p with respect to t at constant v. From the relation dg equals negative s dt plus v dp, the Maxwell relation is the partial derivative of s with respect to p at constant t equals the negative of the partial derivative of v with respect to t at constant p. And these relations are particularly useful in situations where entropy changes are difficult to measure directly but can be inferred from more easily measured quantities such as pressure, volume, and temperature. Factoren. Real-world applications of thermodynamics and entropy. The principles we have discussed this evening have enormous practical importance across a wide range of engineering and scientific applications, and it is worth taking some time to discuss several of these applications in a careful and measured way. Heat engines and power plants. Steam turbines in electrical power plants operate on thermodynamic cycles that approximate the Rankine cycle, which is a practical variant of the idealized Carnot cycle, involving processes of boiling, expansion through a turbine, condensation, and pumping. The efficiency of such plants is fundamentally limited by the Carnot efficiency formula, ETA sub Carnot equals 1 minus T sub C divided by T sub H. In a typical coal-fired or nuclear power plant, the hot reservoir temperature might be on the order of 800 to 900 Kelvin, and the cold reservoir, the environment to which waste heat is rejected, might be at approximately 300 Kelvin. The theoretical maximum Carnot efficiency is then approximately 1 minus 300 divided by 800, which equals 1 minus 0.375, which equals approximately 62.5%. Actual plant efficiencies are lower than this theoretical maximum due to irreversibilities in the real processes. Refrigerators and heat pumps. A refrigerator is thermodynamically a heat engine operating in reverse. Work is done on the refrigerant fluid, and the device transfers heat from the cold interior of the refrigerator, the cold reservoir, to the warm room, the hot reservoir. The performance of a refrigerator is characterized not by efficiency, but by its coefficient of performance, defined as the heat removed from the cold reservoir divided by the work input. The theoretical maximum coefficient of performance for a refrigerator operating between temperatures T sub C and T sub H is given by T sub C divided by the quantity T sub H minus T sub C. A heat pump, which heats a building by extracting heat from the cold outdoor environment and delivering it to the warm interior, has a coefficient of performance defined as the heat delivered to the hot reservoir divided by the work input, which has a theoretical maximum of T sub H divided by the quantity T sub H minus T sub C. Information theory and entropy. In 1948, Claude Shannon, in his foundational paper on information theory, introduced a concept of entropy that is mathematically identical in form to the Boltzmann entropy. Shannon's entropy of a probability distribution is defined as the negative sum over all possible outcomes, I of p sub I times the natural logarithm of p sub I, where p sub I is the probability of outcome I. This quantity measures the amount of information, uncertainty, or surprise associated with a random variable. The formal mathematical identity between Shannon entropy and Boltzmann entropy is not merely a coincidence. Both quantities measure in their respective domains the degree of uncertainty or disorder in a system. The connection between thermodynamic entropy and information was further explored by Rolf Landauer, who in 1961 showed that the erasure of one bit of information in a physical computing system must dissipate at least Ka sub b times T times the natural logarithm of 2 units of energy as heat, a result known as Landauer's principle, which establishes a fundamental connection between information processing and thermodynamics. The arrow of time. Perhaps the deepest and most philosophically significant implication of the second law of thermodynamics is what is known as the thermodynamic arrow of time. The microscopic laws of physics, classical mechanics, quantum mechanics, electromagnetism are all symmetric under time reversal. They do not distinguish between past and future. A film of 2 billiard balls colliding looks equally plausible whether run forward or backward, yet at the macroscopic level we observe a clear directionality to physical processes. Heat flows from hot to cold, not from cold to hot. Gases expand into a vacuum. They do not spontaneously contract. Broken eggs do not reassemble themselves. This directionality is encoded in the second law of thermodynamics and the principle of entropy increase. The direction of increasing time is the direction of increasing entropy. This is a profound and as yet not fully resolved issue in the foundations of physics, touching on questions about the initial conditions of the universe and the emergence of macroscopic irreversibility from microscopically reversible laws. Tusti, summary of the laws. It may be useful, as we draw toward the conclusion of this lecture, to briefly summarize the 4 laws of thermodynamics in their most concise formulations, so that the listener may have a clear and organized recollection of the material we have covered this evening. The 0th law. If 2 systems are each in thermal equilibrium with a third system, they are in thermal equilibrium with each other. This law establishes the concept of temperature and makes temperature measurement possible. The first law, the change in internal energy of a system equals the heat added to the system minus the work done by the system. Equivalently, energy is conserved. It cannot be created or destroyed, only converted. A perpetual motion machine of the first kind is impossible. The second law, the total entropy of an isolated system can only remain constant or increase. Heat does not flow spontaneously from cold to hot. No heat engine can be more efficient than a Carnot engine operating between the same 2 temperatures. A perpetual motion machine of the second kind is impossible. The third law, the entropy of a perfect crystal at absolute 0 temperature.